So, as Alba mentioned, what I'm going to talk to you about today is specifically seismic denoising using self-supervised methods. I'm going to spend sort of the first half of the presentation discussing these self-supervised procedures. And then I'm going to spend the other half focused on how we can use explainable AI methods to actually help us in our denoising. So not just to understand what's happening, but to use that understanding to help make better denoising algorithms. So I wasn't sure if everyone is from the seismic domain. I'm assuming not. So I just want to say that everything I'm going to present today is about the statistical relationships between signal and noise. So I'm going to show all my examples in the seismic space, but it is technically domain agnostic, what I say, as long as the statistical relationships between the signal and the noise remain how I'm telling you they have to be. So as long as the assumptions hold, then what I'm presenting is not strictly stuck in the seismic world. So I always think it's good to start off with a definition of noise, particularly in the seismic sphere. We have a signal, the seismic signal, but we say that data is our signal plus the noise. And noise, in my definition, is anything present within the data other than our desired signal. So it so going for today, what I'm going to be talking about, the first reflection is the signal I want to see, and noise is everything other than this, even if it looks coherent and like seismic. And in the seismic world, our noise comes from everywhere. So as I said, we do have noise that originates from our source itself, but you also have noise from all these other activities going on. For example, passing traffic from anthropogenic sources like, for example, a power station. Particularly if you're thinking of CO2 storage, you would hopefully have a scrubbing power station nearby, and that's going to make a lot of noise. And these noises all have their own statistical properties. They all have their own source signatures that look quite different. So if you think about a car passing, it's going to be a quick like whoomph through your data, as opposed to, for example, the power plant is going to be a constant sort of something sound. So this is where it gets quite complicated for denoising, because you're not talking about one single noise with its own characteristic. It's a noise field. I think like the audience today, you all know what deep learning is, but just to remind you, traditionally how we would do deep learning for denoising is that we have some training data, hopefully lots of it, as you see on the left here. And with that noisy training data, we hopefully also have a paired clean example, which is what you can see on the lower right down here. Now you'd pass your noisy data to the network does its prediction, you compare the prediction with the clean target, and you'll get your loss function. You're going to use this to update the network's parameters, and then hopefully this loss is going to converge as the network starts to give you better and better predictions. So where the data, the predicted data is as close as possible to this target clean example here. Then for inference, we give it a new noisy example, we pass it through that trained network, and fingers crossed, it gives us the denoised product. So yeah, just a quick recap. You'd have, for the training, you have your target data, you have your input, and you're going to compute the loss between the prediction and the targets. The challenge is that in seismic data, we actually don't have a target, right? And this is, again, not just stuck to seismic. There's a lot of cases where you collect data and the data you collect is inherently noisy. And there's a big challenge here because you don't have any clean target that you can use for computing your loss against. Typically, there are two routes people have taken in the past where they've tried to make labels, okay? So the challenge that we have is that we don't have labels, we don't have this ground truth clean data. And the initial solution people came up with is, okay, well, we'll just make these labels. And there's two ways that this has sort of been approached. The first is to utilize synthetic data. It's really common for us to make waveform models So this is something that's sort of the bread and butter of geophysicists. One of the great things here is that synthetically, we can generate almost as much data as we wish, right? Which is great for training deep learning models where we need lots and lots of examples. The other really good thing here is that you are 100% sure it's noise-free, right? You have generated this, you know exactly what is in it. And you know, particularly from the waveform side, that no noise has been added from an environmental point of view because it's synthetically generated. The challenge is, with synthetic data, it's quite hard to make it realistic. You'll read a lot about trying to make synthetic data look like field data. And this is a big hurdle when you're training a network because you train it and you optimize its performance for synthetic data. And then you have a network which you're not quite sure how it's going to handle field data when you bring in these new characteristics of slightly different source signature, definitely different field noise. So you can't know exactly how your network's going to perform. The other way people have approached it is to pre-process field data. And this takes away that challenge, which I just mentioned about making it generalizable to field data, because now we do have the exact same source signature, we have the exact same signal in there. But one of the big challenges here is that when you pre-process data to get your labels, so say, for example, you run a non-local means or something, so you just do a traditional denoising approach to get your training labels, you are now training a network to go from the raw noisy field data to the product of your non-local means. So you're actually limiting the performance of your network. You're limiting how well it can work to how well the non-local means has worked in giving you this training target. So today what I'm going to be presenting about is an alternative solution. So instead of saying that the solution to having no ground truth is to make labels, the alternative solution is to reframe the task so that labels are no longer needed. And this brings us to the field of self-supervised methods, which I think have become quite popular sort of starting in 2019, and definitely in the last 2 or 3 years, they've had a really big burst. So what is self-supervised learning? Self-supervised learning is a family of deep learning methods where we can learn from unlabeled data. I think that Jan LeCun says this much better than I could possibly explain it, so I'm just going to read what he says. In self-supervised learning, the system learns to predict part of its input from other parts of its input. So in other words, a portion of the input is used as a supervisory signal to a predictor fed with the remaining portion of the input. Just in case anyone's wondering who Jan LeCun is, he is a complete expert in this field. He's really one of the top people working in deep learning. So when he's talking about this, I'm very trusting of his content. There is different fields of self-supervised learning, and this would be representation learning, contrastive learning, and blind spot networks. And the field which I chose to focus on for the denoising procedures are blind spot networks. So the blind spot denoising approach was proposed originally in 2019. This particular approach, called noise to void, was proposed by Alexander Krull and his co-authors. And what they saw is that it's not just seismic, as I'm always coming from the seismic field, but it's not just seismology that faces this. Any waveform modeling, but also natural images, in many fields, they just do not have clean targets. And actually, they don't even have repeatable signals. So you couldn't use an approach such as noise to noise because the second shot of your signal is not the same as your first. And what's proposed is a self-supervised method which works on a single image on its own. And their method is called noise to void. And like all self-supervised methods, the real benefit here is that no labels are required. So you can see that for the first two data sets that I show here, then these data sets actually have a ground truth. And in the instance where there is a ground truth, then you can see that the traditional deep learning approach is outperforming noise to void. But in the 3 other benchmarking data sets, the bottom 3 here, there is no ground truth. So it's not possible to use a traditional deep learning procedure here, like a standard supervised procedure. And in this instance, then we are getting what I think is quite a nice denoised product, right? You can see that a lot of random noise has been removed, particularly in this 4th example. And we're doing that on only a single image, which is the real strength of noise to void. How does it work? Basically, what you have is some noisy data, and what you desire is some clean data. And how the blind spot works is that it's going to hide a central point, so in here the red pixel, from the network. And the network is going to have to use all those surrounding pixels or the surrounding data points in order to predict this central value. So we have the assumption that data is coherent signal and incoherent noise. So make an assumption that there is no relationship of the noise between pixels, then the network can only learn to predict signal components. So the theory is that a central noisy value can be recreated using the noisy neighboring values, so this raw neighboring values, where the noise is independent, then the predicted value will only contain that signal information, okay? Because the noise is independent, you cannot learn to predict it. And so to get the network to reach that lowest level of the loss, to reach sort of minimum, then it's predicting the signal as well as it can, and it stops trying to predict the noise. So in reality, or in practice, how can you ensure that the network does not learn to use the central value? So this is the methodology proposed for blind spot denoising. And I was going to talk you through how we ensure that the network doesn't see that middle pixel that I showed as like the eye blinding. We start off with raw common shot gather. It's contaminated here by random white Gaussian noise. For the purposes of training the network, we need to have loads and loads of examples. So what we do is we patch up that shot just to give us more examples for the network to learn on. The next stage in the pre-processing is active pixel selection. So here we're choosing what points we do not want the network to see during the training procedure. So to ensure the network does not use those active pixel values, we're going to replace them. So this noisy patch corruption, basically what we're going to do is for every active pixel that we've selected, we're going to replace its original value with a value from somewhere in its neighborhood. This gives us these noisy patch corruptions, which can be passed to the network, which do not have the original values of the active pixel in them. The network is going to give you a prediction of what it's been passed. So a prediction of the data, hopefully denoised. And for computing the loss, what we're going to do is we're going to have the target, so that raw noisy patch that we've already chopped up before. You see, once we chopped it, we just pass it across for computing the loss. So you're computing the loss against itself, and we're only computing the loss at the location of the active pixels. This means that only for the pixels whose value was replaced, so the pixels that the network never saw the original value from, only at that location are we going to use the loss. Okay, and this way we can ensure the network never learns to use a central pixel when predicting itself. Instead, it learns to use the neighboring pixels. So I think I talked a lot already. I just want to give you some examples now. So for example, for random noise suppression, the assumption I am holding here is that no relationship exists between noise across the data sets, okay? So the pixel-wise noise is completely independent. Here is a synthetic shot gather with white Gaussian noise. To do a few sort of tricks, not really tricks, but like to get the best out of the network, then I pre-process the data slightly. I just use log1p scaling. I normalize the shot so that we don't have this huge range of amplitudes that we sometimes see, and that my later arrivals, so the signal in the later part of the shot, its amplitude is just boosted slightly because that typically has a much lower amplitude. So we do some pre-processing. Then for the masking, what we do is 25% of each patch is going to be selected as active pixels. Now, these are just randomly chosen, but 25 of the pixels within the patch are active pixels. We have a simple UNet for training and simple MSE loss function. And this is a denoise product. So I just want to emphasize that this is done in a fully self-supervised manner using just the noisy shot gathers, okay? So there was no clean target used at all. We just used that noisy input data. We've removed the active pixel's original value and trained the network in that manner. And this is the denoise product. Here you can see how much noise has been suppressed. And on the right, you can see the difference with the clean. So this sort of gives an indication of how much noise remains and also if the signal is damaged, because it's really important to us that whilst we wish to suppress as much noise as possible, you really don't want to damage the signal. So for instance, where that amplitude is particularly high, right at the top peak here, you can see where the arrivals first occurred. I do think we have a slight bit of signal damage just because those amplitudes are much higher than the majority of the signal that the network's been exposed to. But I think we can agree that for a self-supervised method, so one which uses just itself, the raw noisy data for training, this is a really good result for denoising. I want to give you a field example, again, for random noise suppression. So we're just using these active pixels, single blind spots. Again, I use the same training parameters, so 25% of my patches are selected as active pixels. Because I only have one depth slice, I only have one image here, so I've had to patch it up a little bit smaller. You'll see that I have patch size 64 by 64. It means I have slightly less data, but that's okay. I also have a slightly smaller UNet, so we are constraining it slightly more. And here's the denoise product, okay? So you have the noisy data, which has been used for the training. And then after training the network in a blind spot manner, this is how much random noise was removed. I think if you follow some of the horizons, you can really see that it's sharpened it up. But the best way to see it is actually to show the difference between the two. So on the right here is all that random noise that has been extracted from this depth migration. As before, you can see a tiny bit of signal leakage on these higher amplitude signals, which again, I think is just a case of needing to balance out a little bit more the difference in the signal amplitudes which we're seeing across the image. But in reality, random noise is not very common. We actually normally have some relationship existing in our noise across pixels. So I want to explain to you how we can adapt the methodology of blind spot denoising to handle this. And it's super simple, okay? So the way that blind spot worked was that we removed the pixel itself because that would have told us how we could predict the noise as well as the signal. For when you handle coherent noise, what we're going to do is we're going to look at the correlation across the pixels and see where the noise is correlated with each other. So we would select an active pixel, for example, a red box here. And if you're using colored noise, maybe we have filter length of 3 and 3. This is just simple spatial temporal Gaussian colored noise. Instead of working with a single blind spot, you're going to make a blind mask, which is going to cover all pixels where the noise is correlated with that central pixel's value, okay? So basically we are removing the original values of any pixels which would allow the network to learn the central pixel signal and noise volume. So here's just 3 examples. I said colored noise. It would, if this is a 3x3 colored noise, you would just have a square. Or something like, we call it coupling noise. It could be a trace-wise noise. Perhaps you have a dodgy receiver. You would mask the full trace, so take away all of the information of one trace when predicting itself, and you use the neighboring traces. So this is just a trace-wise mask. And for linear event noise, this could possibly be, for example, an earthquake. So a signal that's come from somewhere very different. It has a different move out, as you can see. Then you just do a new mask, the linear mask as shown there. So the workflow for blind mask denoising is really similar to blind spot denoising. Again, we would patch the data. At this point, instead of just selecting the active pixels and replacing their value, what we're going to do is we're going to select the active pixels and we're going to put masks on top of them. Okay, and this is going to ensure that any useful noise information is removed from that noisy patches before they are passed into the network. Again, we're going to pass the corrupted patches to the network. We're going to compare the prediction with the original raw noisy data patches, and we're going to compute the loss on only the active pixels. So let me give you the example for colored Gaussian noise. I used the same pre-processing as before. In this example, I used a lot less active pixels because what you're doing now is, because you're going from a single point to a masked area, you're corrupting a lot more of your patch. So you're actually taking out a lot more information. In this case, it's better off if you lower the number of active pixels so that you ensure that there's still enough information available in the patch that the network can learn how to recreate the signal. Apart from this, everything remains the same as it was for the blind spot example. And here's the denoise product. So yeah, again, on the left is the noisy, then there is the denoised, which has been created using only the noisy example for training. We have the difference between the noisy and the denoised. You can see that a huge amount of data has been removed, and then the difference with the clean. You can see that a lot of data has been removed, a lot of noise has been removed, but there is a little bit of background noise, which is persistent. And we're also seeing that there is some noise within the shot gather area itself. For another example would be something called time correlated noise. So this is noise which is trace independent. It's just a straight line. So at any point, it's correlated to the noise in the y-axis, but it's independent across the x-axis. And this means it's really simple for us to make a mask, because for our noise mask, we just would have a single width of one full way up the y-axis, and then same training parameters and everything as before, same network. And here's the denoise product. So we have, I think, taken out almost all of that trace-wise noise. You see that the denoise product is really clean, particularly in comparison to how noisy that original noisy data was. Again, just to emphasize, there is no target here beside the noisy data that we have originally to work with. So I just want to give a few other examples from the literature where they've done, for instance, a more complex mask design. For example, Lucas Mosser and his colleagues, they looked at dipping noise and they came up with their own mask. It's just this angular linear mask, which will hide the effect of noise, dipping noise. They've produced some really good results there. You have the trace-wise noise suppression for common shot gathers, and also for ground roll suppression. Sishu Lu has come up with some great results where she has developed a fan-based mask, which takes into account the move out that we would expect to see for ground roll, and uses this for ensuring that the network cannot learn from any how do you say, from any pixels that would be along that same move out line. So I think that this sort of stage is quite well proven now. There's been quite a lot of examples of both blind spot and blind mask denoising, and within the seismic field, we think that this self-supervised way is given some really good results so far. However, coming into the last part of my presentation, we do still have a few hurdles, okay? So for the next sort of bit, I'm going to focus on the mask design specifically. So the issue is that all of these examples, that I just showed, we have gone in, or the authors have gone in, they specifically look at a type of noise that they're trying to suppress. We look at the statistical properties of it, we look at the move out, and we use this to design the mask, okay? So it's a way that we've done it based on our experience as domain experts, or we've done it based on some pre-analysis of the data itself. And what I want to show is how you can actually automate this mask design with some methodologies from explainable artificial intelligence. So I think this is how most people think of machine learning. I don't think everyone on the call thinks this way, but I think traditionally this is how a lot of people think of it, right? We have some input, we have some big black box, and then we get some output. And so many times I hear, I don't know exactly what is done, but it gave good results. Or my favorite one is, oh, it's magic. It's not magic, okay? And I want to leverage that fact to help my denoising process. So what is explainable AI? Basically, it's a set of tools and frameworks which help us to understand and interpret the predictions made by our machine learning models. And if we can understand what the network is doing, then we can tailor how we utilize it to make sure that it's working in the best way possible for us. This leads me to the white box. If we start to think of machine learning as just some function of we give our input, we just do some function, and we get the outputs. Where do I think that explainable AI can help in blind mask denoising? The issue with blind spot denoising is that we fail when we have coherent noise, because the network is going to learn the signal and the noise. So blind spot denoising is that first approach that I showed to you, where we select one active pixel and we replace that active pixel's value. So all neighboring pixels can be used for recreating a central value. And if there is coherency within the neighboring range, of course, that central pixel will, its prediction will contain both signal and noise. Blind mask denoising, so where we've designed this noise mask, which will hide this influence, the challenge there is that requires the mask. And that requires us to dig quite deep into what are our noise properties, what are we experiencing in the data set itself. So my hypothesis is that using an explainable AI component on blind spot denoising can identify the pixels that teach the network noise, and we can use this to guide our mask design or even to automate it. And this brings me to a recent paper by Mohan and his co-authors, where they talk about the Jacobian matrix analysis. So basically, you can think of the neural network as we have some input image, X. We have, here would be our neural network, so our f of theta, for example, and we have our output image, which is hopefully a denoised product. In this manner, the Jacobian matrix would be the weights of our network. It's the gradients of the weights of the network. And there's some biases. If we do it as a bias-free network, I am sure you can see where this is going. This becomes a linear problem where it's locally linear, okay? So for a single input image, we are just doing the dot product with the Jacobian matrix of the network to give us our output image. I think this is much easier. Oh, okay. So the Jacobian matrix informs us how much each individual pixel in our input image contributes to each pixel in the prediction, okay? Now, I think it's much easier to visualize when we start to think of it more as matrices. At least I find it easier this way. The input and the output image here have been unraveled. So they're nx by nt, or if you work more in images, it would be nx by ny. So this is just the dimensions. I've unraveled it. We have some output image, and we have one pixel here, for example, y of I. To understand how we got the product that we got, the predicted value for y of I, it's simply a row of our Jacobian matrix multiplied by our input pixels, okay? And as you can see, that is the Jacobian matrix there. So we now know for each input pixel how much it has contributed to the output pixel. If you reshape this Jacobian row, we can now start to see sort of the heavy influencers that have played a strong part of the predicted value, okay? Now you could do it for lots and lots of pixels for the output image, and you can start to make a map sort of the pixels which are all strongly contributing to a central pixel's value. And this is what you can see here. It's just a heat map. It's the average of the Jacobian rows. You can see I've taken each Jacobian row, which corresponds to a different output image. We just reshape them, and we're going to not just reshape them, but we're going to center it such that the active pixel is always in the middle, okay? Because the active pixels are different locations. So you can think of this as like the active pixels location, -1, +1, etc. Then we can stack them together and take an average and really see that across our full image, what does the network believe are the strong, or what is the network using? It's not belief. What is the network using to predict this central pixel? And this brings me back to how can we use explainable AI for blind mask denoising? So if we can use the blind spot to identify the pixels that teach us how the network learns the noise, we can use this information to automatically make a mask that hides these pixels for the blind mask denoising. And that would be the workflow which I propose with my co-author, Matteo Rabassi. So we have the original raw data. We're going to do a traditional self-supervised blind spot approach as shown in this step 1. Now, the point of this is not denoising, okay? Because we assume we have some coherent noise in the data, actually this training and the inference are probably going to give us pretty much exact same result, okay? The network is being trained in a blind spot manner, which means that it cannot use the central pixel to predict itself. But because the noise is coherent, the central pixel, both the signal and noise component, should be pretty predictable, okay? Now, after we've done the training of the network, we can do the Jacobian analysis, and this allows us to see which were the pixels which heavily contributed to the prediction of a central pixel's value. You can do a simple thresholding on this, so any pixels which have a contribution in total of more than 1% of the value, we could choose to place them inside the mask, which would be this third step of the procedure. And then you use that mask for the self-supervised blind mask denoising. And then you hope that the denoised product would be a clean data set, okay? So you're using that mask, which you've identified in a data-driven manner from the blind spot training. So here is 4 different examples. We have 4 different noises, okay? We have the clean common shot gather on the left. This is just shown for representative purposes. It's not used at all for training the network. We have time correlated noise, which means that the noise is trace-wise. It's only along the y-axis. We have isotropic colored Gaussian noise, which means that it's like a square. It's the same amount of pixels in X and Y correlation. Anisotropic colored Gaussian noise. This is quite common actually in seismic, where we have a slightly longer temporal correlation than we have spatial. And finally, we have something called pseudo-rig noise. This is where we have a constant linear noise coming in at a slight angle, which is just like you have a constant source somewhere that's propagating noise always at a fixed velocity. Now, if we do the blind spot denoising, the blind spot training, then what we can get are these Jacobian heat maps. This is showing us which pixels contribute the most when doing the blind spot procedure. We can put that as a simple cutoff threshold. So this is what the masks would look like. It's not exactly what you would think of when you know the noise, but this is how the data is implying to us it should be done, okay? Now, if we use these masks for the blind mask denoising, this is the product that we get, okay? So if I show you again, this is the original raw noisy data, which is used both for the development of the masks using the blind spot procedure and the Jacobian analysis. And then this raw noisy data is also used in training the blind mask network. And this is the resulting product, okay? So you can see that that's 4 very different noise types. And we have really, we've really well suppressed significant volume of noise in all of them, okay? They've all really reduced the noise, which we saw. So this is the noise suppressed. I think, yeah, as I said, you can really see that we've taken out a huge amount of noise, all in a self-supervised manner. And this is the signal leakage, or the difference with the clean, okay? Here we can see that there is a little bit more signal leakage. For example, you can start to see some correlations, some coherency in the signal, particularly if you can see my mouse, these sections. And this is a challenge because by allowing our masks to become quite big, if I jump back to, you can see that the masks are quite a large area. Now the network must use information, or only the pixels, out with the masked area. So although we've managed to hide a lot of the noise information to the point that the noise has been really well suppressed, by increasing the masked area, we're also restricting the signal information. And I think that's why we end up seeing a lot of this signal leakage towards the end. So in future, perhaps it would be good to lower the cutoff limit, which I selected, and see if we can still suppress an adequate amount of noise without introducing some signal damage into the denoise product. I just want to say, to end with, signal leakage is a challenge for all of these self-supervised denoising procedures. What we see is that because the network is not shown a clean example, it's not shown what it should be returning to us, the network has to infer that itself. And this has resulted in a lot of people discussing signal leakage challenges. And there are 3 approaches which I think are quite promising in how this can be dealt with. I'm not going to dive into them because I don't really have time. But if you're going down this route, I really think you should look into these. So first you have a tailored loss function. And this is where they have expanded the loss such that you're not just teaching the network where the active pixel is, not computing the loss there, but you've weighted the loss so that some of the loss is computed on the full image and some of the loss is only computed on the active pixels. And if you balance that correctly, the authors showed that you could still keep the blind spot methodology, but you could reduce the signal leakage. This is, for an example, where they did have only trace-wise noise, okay? So they do have some really nice areas of their data set, which is clean. Another example is, for example, transfer learning, where we do some pre-training using synthetic data set, okay? If you remember, I started off saying that synthetic data, we can struggle sometimes to make it realistic, make it generalizable. And that's where you use the transfer learning, okay? So you pre-train the network that it learns how to replicate a signal with a similar source signature. And then you can use transfer learning to adapt it to your field data set using always a self-supervised blind spot manner. And the final one is for certain noise situations. So for example, the rig noise example I showed where you have constant noise, or the example which is in this third box here, which is a deblending one. So multiple shots have been simultaneously shot. So you have data which is blended. What you can do is incorporate physics, okay? This is all about wave propagation. If we know the properties of our noise waves, as well as our waves of interest, so our signal, we can use that information alongside blind spot networks or blind masking to help us do the denoising framework, okay? So this example I gave where they incorporate the physics, this is a plug-and-play solution proposed by Lurkin. And for their regularization step, they use the blind mask denoiser. So this is sort of three possible solutions that you could look at for the signal leakage. So with that, I will conclude. I'll stop talking. I just want to say that I hope what I've shown is a deep learning scheme with no labels required. Okay, so we're over this limitation. You do not need to have clean training data. I've shown how where you're using coherent noise, you will have to design a mask, but there are methods such as the example I gave with the Jacobian analysis where we can automate that mask design using the Jacobian analysis. I also ended with discussing a few of the avenues which are currently ongoing for how you can reduce the signal leakage, because as that mask design increases, we did see an increase in the signal leakage. This is a little bit old because obviously we're in 2024 by now, but if you are interested in getting hands-on with the self-supervised noise suppression, I gave a tutorial with my student, Sishu Liu, 2022, and you can see the tutorial on YouTube, and also you can use our code and our data if you want to try it out for yourself. And with that, thank you very much for listening. As I said, Sishu is my student I've been working with, and she's done a lot of work for blind mask denoising for complex noise situations. Also, Dr. Nick Lurkin, he's helped significantly in this work, and he does a lot with blind trace deblending. I want to thank Saudi Aramco for partial funding, and also KAUST, who are incredibly supportive of this research. So thank you very much, and I'm open to questions.